Xiaofeng Wu. I'm a lecturer in space engineering from the School of Aerospace, Mechanical and Mechatronic Engineering, University of Sydney. So the space engineering team at the University of Sydney is a relatively small group, and we are partnered with the School of Physics and other schools, and we are participating in the QB50 project. So what I'm going to talk today is I would like to introduce our payload, and one of the payloads actually, which is the radiation counter, using we call the sugar, which is a pin diode detector, and how we test it and how we use it for other and Inspire 2 mission and for other missions. So first I would like to introduce the sugar and the dosimeter. So basically the sugar dosimeter is the full name is the Sydney University gamma ray dosimeter. So this is the construction of the dosimeter. Basically we use the silicon the wafer and to build the dosimeter. So it's using the pin diode. And then for electronics, so we got the sensor, and then that's the pulse generator. And so in this case, we will count the pulses, and then we use this to determine the radiation level in the orbit or in the near space environment. So this is our final product. This is the sugar dosimeter. So it's about the dimension is about 28 millimeter by 16 millimeter. Actually, I got the dosimeter with me now. So this is an engineering model. So this is not a prime model. So okay, I just carry it anywhere. So it's very robust and can be used in any environment. So I think radiation is important. Like I asked Ian about the radiation testing, because for the mission like 11 years, we need to consider the radiation effect on the space electronics, especially. And what we want to do is we want to measure the radiation level in space, and at the same time, we also want to use the radiation detector for some scientific missions. For example, to predict the space weather. So the dosimeter itself is pretty simple. So it's using the arrays of the pin diodes, and then so this is above. So at the top, it's just the pin diode, and at the bottom, it's the electronics. Okay, so basically the dosimeter itself, including the PCB design, so the PCB, it's less than 10 grams. So the operating voltage. So here it says the 5 watts, which is not right. Actually, this is I got. This is on one of the paper from the Journal of the Radiation Measurement. So we use like operating voltage is 3.3 watts. And the current drain is 2.9 milliamp. So it's very low power consumption. And also, we use the copper 60 to calibrate the sugar dosimeter. So it is the 5.8 counts per minute, or the microsiever. And so we also did thermal vacuum testing. And the temperature range is about from 200K to 333K. And also we did a vibration testing, and using a vibration table built by the space engineering lab. So it can survive from like 2.8 G at the moment. Okay. So we also tested in the microwave environment, and it's working. Okay, so now the reason we start with this sugar dosimetry is because the interest from Germany, a German scientist. So AFCAD is the software tool used for the aviation radiation detection, or for the cabinet crew members in the aircraft. And so the FCAD at the moment, this software tool can be used for the aircraft up to 10 kilometers. And the scientists in the Helmholtz Institute, Munich, in Germany. They are interested to expand the APCAR software to the near space and space environment. So we did the collaboration since 2014, and then we decided to capture the sugar dosimeter for a high altitude balloon launch first. So this is our first testing of our sugar dosimetry. So this is on a high altitude balloon testing. So basically, so what we have is we have a high altitude balloon, and then we got a payload box. So this payload box with all the electronics. So basically, actually, in this payload box, it's a 1-unit CUBESAT. So with all the GPS, power supply, but not with the solar panel. So you can see this figure. Basically, the balloon will burst at 30 kilometer altitude. Okay. So you can see the coverage of the Earth. And so here is we use the APCAR to calibrate the sugar dosimeter. So basically, this is the integration of the counts. Okay, and then this is the data estimated from the APCAR. Okay, so that proves the sugar dosimetry can be working at the near space environment. So we did our balloon launch from a place at the Central New South Wales. So from West Violin. And then the testing, the balloon fly with a distance about 70 kilometers. And the balloon burst at 30 kilometers high. And then we integrate the sugar dosimeter into our I-Inspire-2 satellite. So this is our first technology demonstration in orbit. Okay. So basically, we want to measure the gamma ray dosage in each orbit. Okay. So every 90 minutes for each orbit. And we want to use first is for the solar flare detection. So we know like the cosmic ray is the actual constant. Okay. So when it arrives to the spacecraft, basically the gamma ray rate should be a constant. But because of the solar flare or the solar activity, so the rate may be changing. So that's where indicate the solar activity in this case. So in this case, because we know a lot of space weather is related to the solar activity. So in this case, we can use the sugar dosimeter to predict the space weather. Okay, and most importantly for us or for me is I want to use the sugar to study the radiation effect on the electronics on board the satellite. So we want to study the radiation levels, and we want to use the data to view the materials, or how to study how we can protect the satellite from radiation, or we can how to protect the astronaut or concerning the health of the astronaut. Okay, so at the moment, because the gamma ray detector or the gamma particles in orbit, or especially low Earth orbit, is a relatively small volume, which represents 1% of the total particles arriving in the Earth's orbit. So the second mission, we are working with the Helmholtz Institute in Germany, is we are currently building a proton dosimetry, because in space, the predominant particles are high energy protons. So in this case, we build a proton dosimeter, and next month in May, we will launch another high altitude balloon to capture the proton dosimeter. And this proton dosimeter will be used for another mission I will mention later. So this is our UNSW mission. And we are expecting the data from the UNSW2. And one paper is already prepared, and we are waiting for the data. So this is another mission we are currently working on. So Professor Russell Boyce already mentioned that we have a collaboration with the CQT of the National University of Singapore. And at the University of Sydney, at the end of 2015, we signed a MOU with the National University of Singapore, and we decided to build a satellite together. So which is, I call it SUNAS 1, so Sydney University, and the National University of Singapore. So what we want to do is we want to touch, not like any UNSW at first mission, so we just want to touch their payload, this quantum communication payload, on a single 3U CubeSat. And at the same time, because for the communication between the quantum or two satellites, for the quantum communication needs a very high accuracy pointing. So we are also building the reaction wheel for the high accuracy attitude control. So we are developing this reaction wheel based on the two stages of reaction wheel, basically. So one stage is a normal DC motor driven reaction wheel, and the second stage is actually a piezo motor. We develop our own piezo motor and use this to drive the satellite for high accuracy pointing. And we are expecting the pointing accuracy will be around 0.01 degree, but the eventual goal is for the 0.001 degree. So we already built the satellite bus. Okay, so this is the satellite bus built at our school. And so this is 3-unit CubeSat. It has some sensors, and also our student built a star tracker. So basically, what we have is this ADCS, the package. So got the sensor, star trackers, magnetometer, reaction wheel. Okay. And the payload itself takes about 2 units of the satellite. So, and also recently, we are working together with the University of York in Canada. So working on this mission called the DESCEND mission. Okay, so basically, York University have this concept, which is basically using an electrotether to remove the satellite from the space. Okay, so in their mission, what they are proposing to do is they want to build 2 satellites. One is the small satellite, or the big satellite, 3-unit CubeSat, and the second one is the 1-unit CubeSat. So you know, like in Japan, the Japanese Space Agency already launched a satellite for the electrodynamic tether testing, I think in 2016, but it's actually failed. The satellites are not working. So that's why University of York is interested in how we can protect our satellite, or how we can predict the radiation. So that's why we collaborate together. At the same time, we want to touch our proton dosimeter to monitor the solar activity in real time. And in real time, we want to detect the solar flare. Okay, so that's my presentation.
Okay, thank you very much. Any questions? Yeah, just one here.
The dosimeter that you've been describing, is that going to be sold commercially?
We are an educational institute, so at the moment we are only considered as for research purposes. But if you are interested, it's good to collaborate.
Free's a good price.
Okay, thank you very much. Let's move on to the next one.